and in particular, it's about Boyle's law. Boyle's law tells us the relationship between the pressure and the volume of a gas. So here's our chemistry triangle, and in this lesson we're going to make connections between what we can observe and measure and what's happening to small particles like atoms and molecules, and we're also going to talk about the equation that represents Boyle's law. So the symbolic will come into it also. So here's a balloon, and you know that if you push on a balloon, you can make it a little bit smaller, but after a while you can't make it any smaller because when you push on it, you decrease the volume of the air that's inside the balloon, make the space that the air has available to it smaller, and the air responds by having increased pressure, so it starts to push back and you can't make it any smaller. Now we could keep on pushing and eventually you know that the material that the balloon is made out of wouldn't be able to stand it and the balloon would break. So as we make the balloon smaller, the volume of the air in the balloon smaller, the pressure that the air exerts on the inside of the balloon increases. And that's Boyle's law. As the volume of a gas sample increases, that's a little bit different than what we just did, the pressure of that sample decreases. As the volume of a sample, a gas sample decreases, that's what we did do to the balloon, the pressure of that sample increases. So as one of the things, volume or pressure decreases, the other one increases. They move in opposite directions. And if we were to put that in math or scientific terms, we would say that pressure and volume are inversely related. They move in opposite directions. And this is Boyle's law. So here it is in symbols. As the volume of a sample of gas goes up, the pressure that that sample of gas exerts goes down. Or we could say it another way. We could say that as the volume of the gas goes down, the pressure that gas exerts goes up. Volume and pressure are inversely related. I'm going to go away from our presentation for a minute, and we're going to look at this little demonstration. So here is a simulation that you can get online. And in this simulation we have a box, and in this box we have a few gas particles. We've chosen the number 40 gas particles. And these gas particles, on average, are moving around at the same speed. So the temperature is constant. Temperature is 270 Kelvin. And we can see that as these particles move around, the pressure stays pretty much the same. It varies a little bit because sometimes there's more than one gas particle hitting the side of the container. Remember, that's what causes pressure, the collisions of the particles with the insides of the container. So if there's more than one particle hitting the inside at the same time, the pressure jumps a little bit, but basically it stays about the same. It's in the 0.20 to 0.25 range, more or less. So let's see what happens when we change the volume of our box. So we've got a little guy here, and he's going to help us pull the wall of the box out to make the box bigger. So we now made the volume of this gas bigger. And what happened to our pressure? Our pressure went down from the 0.2 area to about 0.15. So as volume got bigger, the pressure got smaller. The volume increased, the pressure decreased. Volume and pressure are inversely related. Now we're going to ask our little guy to push the wall of the box in to make the volume of the box much smaller. Now notice while we're doing that, we're not changing the number of particles of gas inside the box. It's still the same number of particles. We still have the same temperature. And what happened to our pressure? It went up from the 0.20 to 0.25 area to the 0.30 to 0.35 or so area. So as the volume of the box got smaller, the pressure increased. Again, pressure and volume are inversely related. That's Boyle's law. Just to let you know, that little simulation we looked at came from the University of Colorado. It's on a website that has this address, fet.colorado.edu. It's a free website. Anybody can go there and use their simulations, but they do deserve the credit. They created not only this simulation, but lots of simulations for different kinds of science projects. So here's Boyle's law in the form of a mathematical equation. We can make a very specific relationship. P1 times V1 equals P2 times V2. Subscripts are important. Pressure 1 is the pressure early in the problem, or the beginning of the experiment. Volume 1 is the volume of whatever gas we're talking about at the time pressure 1 is measured. P2 is the second pressure, the pressure that's measured later in the problem, or at the end of the problem. And V2 is the volume at that time. So P1 times V1, the pressure and volume at a particular point, equal the pressure and volume, the product of the pressure and volume at another point later on. Very important to keep our subscripts straight. And what this equation says is that as pressure increases, volume decreases, or vice versa. As pressure decreases, volume increases. Now, Boyle's law only works for sure when temperature is constant. So we're assuming, when we say that P1 times V1 equals P2 times V2, we're assuming that temperature is constant, not changing. And another thing that's not changing is we're talking about a single sample of gas. We're not adding any particles, we're not taking away any particles. The number of particles stays constant. Temperature and the number of particles are constant when we're working with Boyle's law. Okay, here's our expression again. What about units of measure? Well, pressure can be expressed in any units of measure that are normally used for pressure, but P1 and P2 have to be in the same units of measure. And we're going to find out that there are lots of different units of measure used for pressure in different situations. Same deal with volume. Volume can be expressed in any units of volume, but V1 and V2 have to be in the same units of volume. And for us, that's usually going to be milliliters or liters. But it could be any unit of volume. All right. Here's some units of measure for pressure, and these are used at different times by different groups of people. And that's a kind of a historical thing. So sometimes pressure is measured in atmospheres with the abbreviation ATM. 1 atmosphere is normal pressure at sea level here on Earth. The SI unit of pressure is the Pascal, which has the abbreviation PA, but it doesn't get used very often because it's a relatively small unit. And so what gets used more often is the kilopascal, 1,000 pascals, with the abbreviation kPa. And here's a connection that is important, a relationship that's important. 1 atmosphere equals 101.3 kilopascals. We may have to use that sometime. Here in the United States, when we're filling our bicycle tires or our automobile tires, and in other circumstances as well, we measure pressure in pounds per square inch with the abbreviation PSI. There are some times when we might measure pressure, oops, let's move this thing out of the way. We might measure pressure in millimeters of mercury, millimeters of mercury. And millimeters of mercury have the abbreviation mmHg. Hg is the symbol for the element of mercury. 1 atmosphere equals 760 millimeters of mercury. And even though it's an outdated unit, we might come across the unit torr. A torr is another name for 1 millimeter of mercury. Let's try a Boyle's Law problem. Suppose we have a syringe. This is a plastic syringe, a pretty big syringe. It's filled with air to a volume of 60 milliliters at 1 atmosphere of pressure. And we want to know what happens to the pressure, what is the new pressure in the syringe, if the volume is decreased to 40 milliliters without releasing any of the air. So again, this is a plastic syringe. It doesn't have a needle on the end. We can cover the end of the syringe and push the plunger down to make the volume inside the syringe smaller without letting go of any of the particles of gas. temperature does not change in this problem. So this is a perfect time to use Boyle's law. Pressure and volume are changing, but the number of gas particles and the temperature are not. So let's see how we can do this. First of all, let's look at the words of the problem and see what we've got. Well, we've got our volume, 60 milliliters. That's the volume at the beginning of the problem. We've got our pressure of 1 atmosphere. That's the pressure at the time the volume is 60 milliliters. We decrease the volume, the second volume in the problem. V2 is 40 milliliters. And we don't know what P2 is, and we need to figure that out. So what can we do? Here's Boyle's law. P1 times V1 equals V2. And we're going to substitute our values into Boyle's law. Move that up a little bit. So P1 equals 1 atmosphere. V1 equals 60 milliliters. P2, we don't know yet. And V2 is 40 milliliters. So from here on out, it's a matter of doing the math. So if we divide both sides of the equation by 40 milliliters, we can isolate the unknown P2 on one side of the equation. We end up with this expression, P2 equals 1 atmosphere times 60 divided by 40. When we do the math, we found out that P2 is 1.50 atmospheres. So the pressure in this syringe started out at 1 atmosphere, ended up at 1.5 atmospheres. Does that make any sense? It does, because the volume went down from 60 milliliters to 40 milliliters, and pressure and volume are inversely related. If volume goes down, pressure goes up. Let's try another problem. There's a problem about a balloon that's filled with helium. So we put the balloon, put some helium in the balloon. The balloon has a volume of 20 liters. It's at sea level, so the pressure is 101.3 kilopascals. So this time we're using liters and kilopascals, which is okay, so long as we use the same units for V1 and V2 and the same unit for P1 and P2. So our balloon is released and it rises up through the atmosphere until the pressure outside the balloon is smaller. So since the pressure outside the balloon is smaller, the pressure inside the balloon adjusts to make the pressure inside the balloon smaller as well. The new pressure in the balloon, 75.0 kilopascals. We want to know what the new volume of the balloon is. The temperature doesn't change. No air particles are getting into or out of the balloon. Temperature is constant. Pressure and volume are changing. Boyle's law is at work. So our problem tells us that V1 was 20 liters. The pressure at that time that the volume was 20 liters was 101.3 kilopascals. That's P1. V2 is what we want to figure out. And P2, the new pressure inside the balloon, 75 kilopascals. So let's use our values there. Let's put them into our equation. Here's our equation. P1, 101.3 kilopascals times V1, 20 liters, equals 75 kilopascals times our unknown V2. Okay, so now we can do the math. We want to isolate our unknown, which is V2. We do that by dividing both sides of the equation by 75.0 kilopascals. That allows us to cancel out that number on this side. We cancel out the unit kilopascals on the other side. And we have a calculation to do, which tells us that V2 equals 101.3 times 20 liters divided by 75.0. And that turns out to be 27 liters. What happened? Our pressure went down from 101.3 kilopascals to 75. And our volume went up. That makes sense? Pressure and volume are inversely related. So there you have it. There you have something about Boyle's law, the relationship between the pressure of a gas and its volume.